Hello everyone. In this video, I will be introducing regression. After this video, I will post another one that goes into how we are going to assess for confounding for our biostats projects. And so look for that one after you watch this one. And subsequently, I will also go through the regression code that's posted on the class website in Stata. So there'll be 3 separate videos for you to watch. But this one today, I'll be in front of the whiteboard because we're going to be talking about the basics of regression. And just as a reminder, since it's been a few weeks since we thought about this, so far, remember that you and your group have picked a topic that you're going to work on using the campus wellness assessment data. And so we're going to continue using those same topics. We're still going to complete your class project in a slightly altered format for this online transition of the course. And so you've already done chi-square tests. So as a reminder, a chi-square test tests for a difference in proportions between 2 different groups. And as we've said a lot up to this point in the class, the campus wellness assessment has all qualitative variables in it. So they're all categorical responses, meaning there are no numeric, no quantitative variables within the data set. So we are only using chi-square tests to look at differences between variables, or we have only used that so far. But now we're going to move on to regression. And as we talked about briefly in class before we broke for spring break, regression is a really useful tool because with a chi-square test, we are just limited to 2 variables. You can only cross-tab 2 different variables. Regression allows us to get a little bit more complexity in our analysis, which better reflects the reality. So that's the rationale for doing this. We do regression, we use regression models a lot in public health so that we can account for other differences between people besides those that we're most interested in. So I'll come back to that idea, that idea that we want to account for other variables. It's called confounding, and I'll be talking about that later in this video, and then we'll do a lot more in the next one that I post, thinking about confounding variables and how to account for them. But I want to start by introducing what the model is, what the regression model is. And so the notes that go along with this video are primarily the regression notes, although I'll also talk a little bit about the confounding notes as well. So regression is a really broad category of different types of statistical models. We'll only be talking about 2 types, 2 pretty basic types for this course. But just know that there are lots of other ways to make these models more flexible depending on what kind of data you have. Our campus wellness assessment is a cross-sectional survey, so we just have 1 time point. So if you have multiple time points, as we've mentioned before in class, these methods won't work because it won't be correctly calculating your standard error if you have the data on the same person at multiple time points. So there are ways that you can do correlated data in regression models, but those are beyond the scope of this class. So we're going to be talking about linear and logistic regression, and kind of like we did when we talked about t-test and chi-square test, linear regression will be for 1 group of data, and you might be able to guess that would be quantitative data, so it's kind of the parallel of the t-test, and then logistic regression is what we need to use when we have qualitative data like we have in the campus wellness assessment. So it's kind of akin to a chi-square test. So let's talk about what regression is trying to do, what these models are actually estimating. And even if the concept of regression is not familiar to you, I'm going to guess that the foundation that I'll talk about first is, so you may remember from high school or other stats classes, thinking about the slope of a line. So we have data, it might follow a slope that looks kind of like this. So I'll give you a minute to think about what that equation is that describes this line. And if you said, you remembered y equals mx plus b, then you'd be correct. So this is typically what we use to indicate the shape of a line. So y is our outcome here. This is the response variable. Often we'd call it the dependent variable. In general statistics, as I've said before, in biostatistics and in public health, we usually call it the outcome because we're usually looking at health outcomes or the impact of some exposure variable or X on Y. So we're trying to model our outcome, our dependent variable here. And apologies for the lights reflecting here. And so we say y equals mx. So x is that exposure variable. The value of x relates to the value of y. Just try to move this a little bit so you can see it. Still not very good. So x is the value of the exposure here. M, you may recall, is the slope. So when you calculated this by hand, that's kind of that rise over run calculation, the slope of the line. And B is the intercept, so where this line starts on the y-axis. Okay, so y equals mx plus b describes this line, and you already know that, you're familiar with this. And so I just want to use this example to illustrate that linear regression is very much similar to this. It's the same concept as the basic slope of a line that you've calculated before. So the equation that we typically use to indicate linear regression is we still have our outcome over on this side. And I wrote E of y here, E with y in parentheses, and that just indicates that it's the expectation of y or the estimate of y, because we never have perfect information about the outcome and response. So this E of y just is indicating that there's some error associated with this. Our model is going to be imperfect, but we're estimating y. And then on the right side of the equation, we put it in a different order, but the concept is the same. So the expectation of y equals beta naught plus beta 1 x1. And so it's different, again, in the order compared to the y equals mx plus b up here, but the concepts are the same. So this beta naught here is the same as the b in the y equals mx plus b. That's our intercept value. Beta 1 over here next to the x is our slope. And then x is still our exposure variable that we're interested in understanding how it impacts the outcome. So this is still our exposure of interest. All right. So same format, same concept. We just use a different set of, symbols and things to represent what the equation is. And one thing that's worth noting here is if x, if your x is coded so that there is a 0 value in it, it could be a yes/no kind of variable, or it could be something where 0 is a possible value. It could be quantitative or qualitative. But if there's a 0, then that tells you that the estimated value of y for people with no exposure is just equal to the intercept. So it is a useful term when we're thinking about health outcomes, this intercept term, because it tells us what do we expect people to experience in terms of the outcome if they have no exposure. The slope is what tells us, for people who do have exposure, the slope is what tells us by how much more does the outcome increase if they are exposed at a certain level, or it could be how much less. So we have a plus sign here. It's possible for the beta 1 to be negative. And in the notes for this section, I actually give you an example where you might have a negative slope, a negative beta 1. So if we were looking at the relationship between physical activity and weight, for example, somebody's body weight, we might end up seeing that the more you exercise, the lower your weight is. So if this exposure were physical activity, you might expect to see a negative slope associated with that, so that you have some intercept for people's weight in pounds, and then this would be physical activity along the x-axis, and kind of less physical activity and more. And so you might expect to see something like this, where as people exercise more and more, their weight on average is lower and lower. So that would be a negative slope here for beta 1. Okay, so hopefully that feels relatively familiar. And as I said at the beginning, this is linear regression, a linear regression model. And that works when we have quantitative data. And so it's useful for things like, weight in pounds, or number of minutes that people are doing some kind of activity, or potentially even something like the number of healthcare visits, or the amount of cost or the healthcare expenditures for someone. Those are all examples that you could potentially have as an outcome in a linear regression model because they're quantitative measures. But again, we don't have any such measures in our campus wellness data set. So I want you to know what linear regression is and how it kind of connects to the idea of just a general line that you're familiar with. We are not going to be using this for your campus wellness assessment work, and so you won't have an opportunity to do linear regression using our data set. So I'm going to move on to the kind of regression that you will be doing, which is logistic regression. So logistic regression, the good news is the format of the equation looks essentially the same. In fact, the right side of the equation for logistic regression is identical to the one that I just wrote up for linear regression. What changes is what we're estimating on the outcome side. So instead of having a quantitative variable that's continuous at this point, we have categorical outcomes, so different categories of variables. And that is what we're trying to estimate. What's the relationship? How does that outcome, how does the odds of that outcome is what we're going to be estimating change when your exposure levels change. So our measure here, and I'm going to go ahead and erase actually this whole thing now. So now logistic regression, the equation, the basic equation, is instead of the expectation of y, so we're not estimating y as a value anymore. So we are instead estimating the log of pi over 1 minus pi. And pi here represents the probability of having the outcome. And so pi over 1 minus pi, or the probability over 1 minus the probability, that is actually the odds. So that is the odds of something happening. We don't often talk about the odds. It's actually a little bit conceptually difficult to think about. Betting is kind of the classic example of where we do talk about odds, when you get odds on a certain team winning or a horse winning if you're looking at a race. So it's the probability over 1 minus the probability. But the reason that it's useful in biostatistics is that what we really want to know is risk. We want to know, is the risk of the outcome higher for one group versus another? And in many cases, the odds is a pretty good approximation of the relative risk. I will say more later about when this isn't true, but for the purposes of this class, we're just going to assume that the odds ratio is probably a pretty good estimate of the relative risk. Relative risk, because as I'll talk about in a minute, odds is actually, we're not estimating just the odds itself, we're actually estimating the odds ratio. When we do logistic regression, so basically when the exposure is rare, when the outcome is rare, so when people do not often have the outcome that you're looking at, and by rare we usually mean like less than 5% of the time, people in the population, so not necessarily in your sample, but in the population, if we expect the outcome to be rare, so less than 5% prevalence or so, then the odds ratio is a pretty good approximation of the risk, the relative risk for the exposure you're looking at, and otherwise the two start to diverge. So there are other types of statistical methods you could use if you have a common outcome so that you can get a better estimate of the risk, but we're not going to go into them in this class since we're just kind of doing the basics. So we'll still use logistic regression for all of your projects, and basically the way we'll acknowledge that it might not perfectly approximate Risk is that you'll just talk about it as a difference in odds instead of talking about it as a difference in risk. Again, we'll come back to that later. So if it doesn't make sense today, we'll be talking about it more as you go along in your project. Okay, so back to the model here. So we're estimating the log odds of some outcome. And so this is saying log odds of y is equal to, and this is where this side is the same as what I wrote before, beta naught plus beta 1 x1. So still that same right side on the equation. Beta naught is still the intercept. Beta 1 is still the slope. So again, it's telling us by how much does the odds of the outcome change if you're exposed versus unexposed, or if you have different levels of exposure compared to lower levels of exposure. And the really important thing that you need to keep in mind for your project is this is where you need to have a binary or dichotomous variable as your outcome. So it must be just a 0 or 1 variable. So earlier in the semester, we made the binge drinking variable. So if binge drinking were your outcome, that would work well for a logistic regression model. You have either students were classified as binge drinking or as not engaging in binge drinking. And remember, there were different cut points for males and females, and we had to combine 2 variables to get down to 1 common binge drinking measure. And that code is posted on the class website. So that's a yes/no variable. Either they're classified as binge drinkers or not. So that's what you need to create for your outcome variable if it's not already structured that way. So for example, 2 things that come to mind on the campus wellness assessment that are not already dichotomous are sleep and physical activity. So both of those questions ask, the sleep question asks, in the past 7 days, on how many nights did you get 7 to 9 hours of sleep? And the response options are 0 to 1 nights, 2 to 3, 4 to 5, and 6 to 7. So you as a group will just have to decide what you'll need to make is kind of an adequate sleep versus inadequate sleep variable. You could call it adequate sleep. It would be 0 if they didn't get enough sleep, 1 if they did. But you as a group can decide by kind of looking at the literature, seeing what other people usually use as a cut point of enough sleep, and then decide how you're going to reclassify those 4 categories down into 2. Same thing for physical activity. I think the question asks how often people get 30 minutes a day of physical activity, or on how many days in the past week they got 30 minutes of physical activity. Similar response options, so you'll just need to collapse those down. So if you have questions about that, looking back at that binge drinking code is a good example of how to collapse categories down. You want to start by doing a generate statement to make a new variable, and then replace that with 0s and 1s using the categories of whatever your outcome variable is. The exposure, on the other hand, on this other side, can have as many categories as you want. So I will say it is a little bit easier to interpret odds ratios if you just have 2 categories as your exposure as well. But it's not terribly difficult to interpret multiple odds ratios for each level of your exposure. So I will show you an example later when we go through Stata code of how to interpret things, how to interpret output, if you do use a multiple category exposure variable. But this is the basic dichotomous outcome, beta naught plus beta 1x on the right side of the equation. The one thing I didn't include on here is that, again, because we're estimating these outcomes and we recognize that there is bias in the estimates, really these models have an extra error term at the end, a lowercase e. And again, estimating the error directly there are methods to do that, but they're beyond the scope of this class. And so we will, when you write up your final group project, I'll ask you to think about where might there be error in your measurements, but we're not going to try to incorporate it into the model here. So you won't be trying to analyze or come up with a quantitative estimate of what the error might be in your equation. You'll just talk about the quality of the measures, the quality of the sample, and how that might influence your results. So I actually think I'm going to break this video now and start a separate one to talk a little bit more about the actual numbers that you get out with this logistic regression model, specifically the odds ratio and how to interpret it. So for now, that's all. Feel free to send me questions if you have them after watching this video. And like I said, I will be posting more that talk about how to interpret this and how to actually do it within Stata. So I'll see y'all soon.